Welcome everyone. Today we're going to learn how to determine whether a molecule is polar or nonpolar. First, I'm going to try to do this into two steps. According to what you're reading here, the first thing is to use the electronegativity values to predict bond dipoles. A dipole is another word for polarity. So the first thing is you're going to ask yourself if there's an electronegative element. And then afterwards, you're going to use the VS-EPR model to predict the molecular shape, which is what we learned in a previous video. And then from that shape, we're going to determine whether the bond dipoles cancel or whether it does not cancel, and which would make the molecule polar. So what we're going to do is I'm going to split this up into two steps. So first thing is first here. Let's put here number one. To determine if something is polar or nonpolar, first you're going to ask yourself this question: is there an electronegative element? I use the word greedy for electronegative. So is there a greedy element? That's the first thing you're going to ask yourself. And if you say no, then the conclusion is it's nonpolar. If there are no electronegative elements, then it's nonpolar. But here's step two. If yes, then go to step two. And if you look at step number two is you're going to analyze the shape. So you're going to look at the shape. And what you're going to do here is see if the shape is symmetrical or asymmetrical. Okay, so that's what we're going to look at in the next part. If the shape is symmetrical, the conclusion is going to be that the molecule ends up being nonpolar. And we'll talk about why in just a moment. If the shape is asymmetrical, then the molecule will end up being polar. So those are the two main steps. It's basically what's here. Now, you'll notice that when a shape is symmetrical, what's going to happen is the dipole bonds, the polar bonds, they're going to cancel each other out, giving you a nonpolar molecule. However, when the shape is asymmetrical, you'll see that one side of the molecule will be more negative than the other, creating a dipole moment. Okay, that's another word I want you to remember. Dipole moment is basically that the molecule has polarity. It's polar. That's what a dipole moment is. If you see that it says no dipole moment, then we're talking about something that does not have polarity, therefore it's nonpolar. Later on, we'll also look at this statement here that lone pair electrons also can make a contribution to dipole moments. In fact, the lone pairs also is what causes molecules to become asymmetrical. And what we'll learn from step number two here is that if something is asymmetrical, you will see how that will influence the molecule in being nonpolar. So step number one was, is there a greedy element? These are the electronegative elements. Notice the corner over here where fluorine is. Those are the most electronegative elements. I use the acronym FUNCL. And as you can see, fluorine is the most, followed by oxygen, and then chlorine, nitrogen, and if you look, we also have sulfur, bromine, and iodine. Those are also more electronegative elements themselves. But you're going to ask yourself that question if you have an electronegative element, and if you don't, then pretty much it's nonpolar. However, if you answer yes to that, just because we have polar or not polar elements, but electronegative elements, doesn't mean it's going to be a polar molecule yet. We have to look at the shape as part of the second step. So let's talk about symmetry. These shapes, as long as both peripheral elements are the same, they're going to be considered symmetrical. I'm going to give you an example of something linear here. Carbon dioxide is linear. So when you analyze this structure, you're going to ask yourself, is there an electronegative element? And the answer is yes, oxygen is electronegative. So what oxygen does is that it pulls the electrons towards itself like that. The problem is that there's another oxygen on the other side doing the exact same thing. So what ends up happening here is there's two polar bonds, but the way they're oriented, they're pulling on opposite ends. It's kind of like a stalemate, like a tug of war where no one wins. So what happens here is that neither side of the molecule is more negative. Everything remains equally distributed. So this molecule ends up being nonpolar. So it has no dipole moment. Another one would be something trigonal planar. And I'll give you an example here. Boron trifluoride is trigonal planar. And again, as long as the three atoms around the boron are the same, they're all fluorines, this is considered a symmetrical shape. So when you ask yourself, is there an electronegative element? Yes, there is. Fluorine is electronegative. So then let's look at the shape. And this shape is also considered symmetrical. See, these fluorines are pulling at 120-degree angles to each other. And what ends up happening is that they cancel each other's pull. And that's what happens here. So this one ends up being nonpolar. Another one would be the tetrahedral structure. So let's say we had something like carbon tetrachloride here. I'm going to I know it's not in 3D here. And each chlorine has their lone pairs. And what happens here is, if you ask yourself, is there a greedy element? The answer is absolutely yes. The chlorine is the electronegative element. But what happens here is when it's tetrahedral, as long as all of those are the same element, the pull that's going this way is negated by the pull going this way. And the same thing happens over here. This guy has 4 polar bonds, but yet the molecule has no dipole moment. All of these molecules end up being nonpolar. All right? And I'll show you these last 2 shapes, and then I'm going to talk a little bit further and give you some additional examples. Trigonal bipyramidal, same thing, okay, as long as everything is the same. So let's take a look at, let's say we had sulfur. Actually, no, I'm not going to use that example. I'll use that one after. Let's say we have phosphorus pentachloride. And this is going to be one of those exceptions to the octet rule. So let me put the chlorines around the phosphorus. Let me go ahead and draw it already. And again, you have your lone pairs around the chlorines. But notice that all the atoms are the same. When you ask yourself the question, is there an electronegative element? The answer is yes, the chlorine. And then what ends up happening is that the way that these guys are angled away from each other, they end up canceling their pull. So this ends up having no dipole moment. And then on the bottom, the same thing can be applied. Here's where I'm going to draw sulfur hexafluoride. And the same thing happens over here. Okay. I'm not going to bother writing the lone pairs for the fluorines. Each fluorine has 6 dots. But you know, I didn't draw this very well, but look, these will cancel, these will cancel, these would cancel. These are 3-dimensional molecules. The point I want to make here is that if they are symmetrical molecules, that the whole molecule will be nonpolar, despite the fact that it has polar bonds, because the sulfur and the fluorine is way more electronegative. So they all possess polar bonds, but the symmetry ends up causing the molecule to be nonpolar. Now, there is an example I wanted to use. Let's go back to the carbon tetrachloride here. We said this is nonpolar, okay? As long as all the elements around that carbon are the same, it's symmetrical. The minute that one of those elements changes, so let's say I decided to change one of the chlorines for a hydrogen, the symmetry is completely lost. So now think of it, these two cancel each other out. This one's pulling this way, but you got nothing pulling on this side. This side ends up being more negative. This is the symbol we use. This is partially negative, and this side is partially positive. Okay, that's what polarity means, that it has a partial negative side and a partial positive side. There is unequal distribution of electrons. So the minute one of those elements changes, it is no longer polar. I'm sorry, non-polar. This one happens to be polar now. Okay? And the same thing could be said with, here's a linear. Okay? But in order for this to be symmetrical, both sides have to be nitrogens or hydrogens, for that matter. You have nitrogen on one side and hydrogen on the other. Think of it as if you put an imaginary mirror. This side on the left does not see it's the same thing on the other side, doesn't see itself. And here, nitrogen is a greedy element. It's electronegative, so there's a pull going this way, but there's no pull going the other way. So this one ends up being polar. Now, something that will always be symmetrical would be your diatomic molecules like fluorine, chlorine, oxygen, nitrogen, bromine. Okay? These are all, pretty much electronegative elements. We can use fluorine as an example. But all diatomics, and that includes hydrogen and iodine, all diatomics are nonpolar, and the reason is that they are symmetrical. So you have here a fluorine with another fluorine. We'll put the lone pairs here to draw it accurately. And yes, this fluorine's pulling this way, but this one's pulling with equal strength. So they end up negating each other. They cancel each other out. And all diatomics end up being nonpolar because they are symmetrical. Now let's talk about asymmetrical. The minute you introduce a lone pair, you totally lose the symmetry. So here's an example. We'll use water to start off with. Everyone is familiar with this bent structure of water. And what happens here is water is the electronegative element. So you have the oxygen pulling that way, and you have this oxygen also pulling that way. And notice even, and this is something I mentioned earlier, even the lone pairs contribute a bit too. See, the lone pairs are also pulling up slightly, or at least at an angle. Actually, they're pulling more at an angle. Let me go ahead and fix that. And the point is that the oxygen side of the molecule is going to be more negative than the hydrogen side of the molecule. And this shape is totally asymmetrical. So water ends up being a polar molecule. Let me give you a couple of other examples of the lone pair throwing off the symmetry. Ozone is a molecule that has resonance. It's bent with one lone pair. Okay? And I'll you know what I'll do? I'll go ahead and draw the other resonance structure so you can remember what these look like. So we got a double bond here. And when you look at ozone, the oxygens really there's not much of a pull here. The oxygens are the same. So people ask me, well, if you have, like a diatomic, right? A diatomic, like let's say oxygen, we can use oxygen as a perfect example here. When you have O2, it would look like this when you draw it. Now, this is linear, and this pull cancels out this pull. So oxygen as a diatomic ends up being nonpolar. Yet when you look at experimental evidence, you'll see that ozone has a polarity. Now, I am going to go on record by saying it doesn't have much of a polarity. It's slightly polar. And here's the reason why it's slightly polar. Even though they're all oxygens and they're all battling against each other and they kind of stalemate, that lone pair at the top is the difference maker. Because of this asymmetrical shape, this portion on the top of the molecule has a slight pull this way, which causes the symmetry to get distorted slightly, and it causes this to have a slight polarity. So it ends up being polar, slightly, by the way, and that has to do with the asymmetrical shape of this molecule due to that lone pair at the top. Now let's look at some more traditional ones. Ammonia, when you draw ammonia, it's trigonal pyramid or pyramidal, and look at this, there's a lone pair there. The greedy element is nitrogen. So notice how all the arrows are pointing towards the middle. They're all pointing to nitrogen, and this, if you want, you could even say this is pointing slightly up. Now notice all the arrows are going towards the center. It makes the center of this molecule slightly negative and the periphery slightly positive. So this molecule, because of that lone pair, also is polar. Okay? Let's take a look at another one here. We have, if you recall, if you have 5 bonding domains, we have the trigonal bipyramidal electron geometry. But look what I'm going to do here. I'm going to pick this molecule, and when we draw it, it ends up looking like this, and it has a lone pair. The minute that you introduce that lone pair, you have lost the symmetry here. This is not symmetrical. Notice the lone pair's on one side and not at the other. And fluorine is the electronegative element. You do have a pull going this way, a pull going this way, a pull and a pull, but this also contributes a slight pull. And this one, if you remember, is the seesaw molecular geometry. Because of that lone pair, this structure ends up being polar. It's not symmetrical. Okay? Let's take a look at another example. We have the square pyramidal would be a shape, and I'm going to do a generic one so you could see here. When you have all of these being the same, these are just putting X here for a generic. When you have all of these being the same, this is going to be nonpolar. This is considered symmetrical. This is octahedral. Now what I'm going to do is I'm going to show you, this one right now is octahedral, not only the electron, also the molecular geometry. So what I'm going to do is I'm going to remove one of these bonding, and I'm going to replace it with a lone pair. And the minute I do that, this is now no longer the octahedral molecular geometry. It's now square pyramidal. And this lone pair throws off the symmetry. So this one would be now considered polar. Okay? So notice how having a lone pair messes up the symmetry. Now, in chemistry, you're always going to see that there's exceptions to these rules. There are 2 structures that have lone pairs. However, the way the lone pairs are arranged keeps the molecule being symmetrical. Let me show you what I mean here. There are 2 shapes I want you to take notice of. One is a linear shape that has the trigonal bipyramidal electron geometry. Okay, this is the molecular geometry. And I'm going to, if you remember, there's a shape that looks like this. Notice it's linear. And it had 3 sets of lone pairs arranged symmetrically around that central atom. And believe it or not, even though these have lone pairs, the way the lone pairs are situated, they cancel each other out. And let's say this was an electronegative element, these would cancel each other out. Let me give you an actual example. You may remember we did one like this. This is a real example here. This is linear. It has 5 domains, so the electron geometry is trigonal bipyramidal, but the molecular geometry is linear. But this structure ends up being nonpolar because this electronegative element cancels out this one, and the lone pairs are 120 degrees to each other. They also cancel out, so it ends up being nonpolar. Okay, so that's one of the exceptions. Now there is one more that I'd like to show you, and this one is the octahedral, octahedral electron geometry. So I'll do a generic one here. Whoops, let's put an A there. So let me go ahead and draw this like this. This has 6 domains. Now, this one, the molecular geometry, is square planar. Now, the way the lone pairs are arranged, they're on opposite sides of each other. If you just by looking at this molecule, you could see the symmetry. So what happens here is whatever pull this one has, it's negated by this one, and this one is negated by this one. But even the lone pairs, which contribute to the pulling, they are opposites to each other, so they also cancel out. So the square planar and the linear that I mentioned before, although they have lone pairs, are considered symmetrical shapes. Here's an example of a square planar. You probably remember doing this one before, where you had the fluorines out here. Let me fix that. And you can see, I didn't bother putting the lone pairs around the fluorines, but you could see how this ends up being nonpolar due to the symmetry. Okay? So when you look at symmetrical shapes, okay, we can make a list here. These shapes, as long as all the atoms around the central atom are the same, they have to be identical, they're always going to be non-polar. And we mentioned linear would be an example, okay? And I'm talking here about the molecular geometries. We mentioned linear, we mentioned trigonal planar. Hang on a second. Trigonal planar is another one here, okay? We went on to say also the tetrahedral, as long as all 4 atoms are the same. Okay, we also have trigonal bipyramidal, okay, and the octahedral. In the video, I have shown you examples of all of these. These are all considered symmetrical shapes. Now, none of these have lone pairs. These are all bonding pairs. Okay, now let me add now the 2 exceptions that are also nonpolar, even though there's the presence of a lone pair because of the symmetry. Whoops, let me fix that. Because of the symmetry. And it's the 2 that I just mentioned, the linear and the square planar. Okay, and when I say the linear, we're talking about the linear that is trigonal bipyramidal, which is this one over here. And the square planar would be this one over here. Notice how everything is symmetrical, including the lone pairs. Okay? Now, the shapes that are asymmetrical and will always be polar are the following. We got, these are all going to be considered asymmetrical shapes. Therefore, they're going to be all polar. And we have bent. There are 2 types of bents. You have the bent that has 1 lone pair. And then you have the bent that has 2 lone pairs, such as water. We saw ozone earlier as the one with 1 lone pair. So the bent is going to be considered an asymmetrical shape. Okay. We also have the trigonal pyramid. Okay, that one's going to be also, and I can draw it like this. That throws off the symmetry there. Trigonal pyramid. Okay, let's take a look at the last ones. I'll put a new page here. We have the seesaw. That one's also going to be considered asymmetrical shape because of the lone pair. Like that. Okay. We also have the square pyramidal. This one has 5 bonding. 1, 2, 3, 4, 5. And there's the symmetrical shape being distorted there. And the last one that I didn't mention earlier, which is also under trigonal bipyramidal, is the T-shaped structure. When you look at the T-shaped structure, it looks a little something like this. It has 5 domains, 3 are bonding, 2 are non-bonding, and the lone pairs do contribute. You know, they do throw off the symmetry. They do cause this to be polar. This is considered asymmetrical. Okay? It's the linear one that ends up being non-polar. So whenever you want to answer a question if something is polar or not, the first thing you do is you ask yourself, you know, is there an electronegative element? For instance, one thing I want to mention is, you know, hydrocarbons. Hydrocarbons such as methane, okay, or propane or octane, any hydrocarbon, if you ask yourself, is there a greedy element? Is there an electronegative element? The answer is no. Therefore, if there's no electronegative element, you're going to end up being nonpolar. And hydrocarbons are considered to be non-polar molecules. Now, if you answer yes to that question, just because there's a polar bond doesn't mean it's going to be polar yet. Okay, look at carbon dioxide again. Then you got to analyze the shape. And you have to see if the shape is symmetrical or not. So in carbon dioxide, there is an electronegative element, oxygen. So then we look at the shape. And when you analyze the shape, this shape is symmetrical, which means that the poles are going to cancel each other out. And at the end of the day, the shape will cause this molecule also to be nonpolar. And we say it has no dipole moment. So just because you have polar bonds, carbon dioxide has 2 polar bonds, doesn't mean it's going to be polar yet. You have to look at the shape. And if the shape is asymmetrical, it will be polar. If the shape is symmetrical, like in CO2, it ends up being nonpolar. Okay?